So this podcast, we're going to be dealing with the very important topic of solubility. Most of the stuff that we deal with in chemistry tends to be in aqueous solution. So whether or not something can dissolve or whether something precipitates is kind of an important piece. So when we talk about solubility and how it relates to equilibrium, the thing that comes to mind is the idea of KSP. So here we have just a definition of solubility, that it's really an equilibrium position. You may have thought about solubility in terms of the saturation point, like at how much can dissolve at a given temperature. And really, that is at the point where the system is at equilibrium. So how well does it dissolve to form an aqueous solution? And we're going to use an equilibrium constant, a solubility product constant, to give us an idea of what that magnitude looks like. And so we call that KSP. And good news, it's set up exactly like KC, KP, KA, KB, KW. It's just another one of those equilibrium constants, but very important number to know when you're thinking about soluble stuff. So when we look at KSPs, you will notice that these numbers are really, really small, because we're talking about not just solubility of things that we know to be soluble, but also the solubility of things that are insoluble. So you're going to find that these numbers are going to be really, really tiny. So first, let's start out just by practicing how do you write a solubility product expression. So for this first example, we've got calcium fluoride, and assume that these things are going to be solid. It's probably going to say that it's solid. When we put something solid in water, now according to our solubility rules, this would be insoluble, but even though it is mostly insoluble, we find that it does dissociate ever so slightly, and when it does, it looks like this. Okay, so that's the equation, the chemical reaction, if you will, of what's going on. So then to go ahead and write a KSP expression, remember that KSP is products over reactants. So this is going to look like that. Don't forget that coefficients become exponents, but then also remember what states of matter we never include in equilibrium constants, and that would be solids and liquids. So for these KSP expressions, you won't have anything in the denominator. Let's look at another example, magnesium phosphate. So if we have solid magnesium phosphate and put it in water, it will dissociate thusly to get 3 magnesium ions and 2 phosphate ions. Then if we were to write the equilibrium expression for this, we have our concentration of magnesium ions cubed times concentration of phosphate ions squared. Okay? So nothing brand new there. Again, just kind of remember that solids are never included in KSP expressions. All right, what types of problems could you expect to see with KSP? Well, this is one type. Mostly the trick kind of comes in just reading the problem. The solubility of copper 1 bromide is 2.0 times 10 to the negative 4th molarity. What is the value of KSP? So solubility is looking at what are the concentrations that we have. So as should be your habit right about now, write out your equation. What's taken place? So we've got copper 1 bromide. So we're going to have a copper ion and a bromine ion. And we're going to set up our KSP value. So keep in mind that when we set up our KSP expression, it's going to look like my concentration of copper times my concentration of bromine. Always write out your balanced equation, so then you know if you need any exponents when you set up your KSP expression. So now what do we know? We know that the solubility of copper 1 bromide is 2.0 times 10 to the negative 4th. And if you notice, it's a 1-to-1 ratio between the copper and the bromine. So since I know my concentration of copper, I therefore also know my concentration of bromine ions. So just do the math here, and we come up with my value for KSP equaling 4.16 times 10 to the negative 8th. Okay, so that's a pretty simple KSP problem. Come on, PowerPoint slide. So the second type of problem would look like this. It would ask, what is the molar solubility of silver sulfide? So molar solubility, think concentration. This time you have a KSP value of silver sulfide. Notice how really tiny that little number is. So what this question is asking you to do is figure out what are the concentrations? What are the concentrations of the ions? So of course you always want to start out by writing your equation, what's going on. So if we take solid silver sulfide and dissolve it in water, it's going to give me silver ions, 2 of them because of my stoichiometry, and 1 sulfide ion. Your KSP expression, set that up so you know what that's going to look like. It's going to be this. And now, in this case, we have a value for KSP, 6.0 times 10 to the negative 51. And since this question is asking me to figure out what is the molar solubility, I'm trying to figure out these concentrations of these 2 particular ions. I don't know them, so I'm going to call them X. Since my silver is in a 2-to-1 ratio with my sulfide, that's going to be 2X, and of course I have to square that. My sulfur is going to be, an X. I saw sulfur, wrote X. Actually, some textbooks, instead of putting an X, will actually put an S just to separate it out from, the icebox tables that you guys have been doing with KAs and KBs. But I will just keep using X, because I like X. Alright, so now we're going to go ahead and solve for X. So we're going to have 6.0 times 10 to the negative 51 equals 4X cubed. And then that tells me X is 1.14 times 10 to the negative 7th. Now in this case, I do have a unit. Please make sure that if you're solving for X, that is going to be concentration, and make sure that you put a unit on that. Okay? So, how does this relate to other things that we've talked about, especially the common ion effect? Really, when you're now dealing with an insoluble substance, questions will ask things like, well, how do you increase the solubility? And what effect does adding in a common ion have on your overall solubility of a substance? So you'll see these kind of written a couple different ways. But really, if you just kind of think about Le Chatelier's principle, that can help you make a lot of predictions about what's going to take place. So let's work through a couple examples. KSP for lead iodide is 1.4 times 10 to the negative 8th. And you're supposed to calculate the solubility of lead iodide in each of the following of these 2 circumstances. Alright, so let's first of all just kind of think about what is happening with lead iodide when it comes to equilibrium. So I'm going to get my lead ions, and, that's right, ignore that, 2 iodide ions, there, getting ahead of myself here. Okay, what's happening is now we're going to take this lead iodide and we're going to put it in a solution, in a 0.1 molar solution of lead nitrate. So we got to think about what is the common ion. Obviously, or hopefully, you see that the common ion is going to be this lead, because lead nitrate is completely soluble and so it will completely dissociate. And if you want to think about this like an icebox table, I'm not going to fill in the C because the change is pretty easy. We know an initial concentration of lead ions is 0.1. My initial concentration of that is going to be 0. So then at equilibrium, this is going to go up. That's going to go up by 2x. Solids we don't include, so we're not going to need that portion of the product. So now if I'm going to calculate my molar solubility for these things, knowing that KSP is, let me set up my KSP expression here. Knowing that KSP is really tiny, and I have the value, 1.4 times 10 to the negative 8th, I can now figure out what the molar solubility is by plugging this in. So now the good news, you can still take that little shortcut, because if you notice, this is a very tiny number, so any change in X is going to be negligible. So we would come up with X equaling 1.9 times 10 to the negative 4th moles per liter. So it's the solubility of lead iodide if we place it in a lead nitrate solution. Now what happens if we put it in a concentration of sodium iodide? In this case, my common ion is going to be the iodine. So again, kind of carrying down from here, in this case, I don't know my lead concentration, but now I have a concentration of iodine. So just kind of thinking ICE over here, just using the same equilibrium. Still don't need the solid because those are never included in equilibrium expressions. Notice that it's plus 2x this time because I have 2 iodine ions for every 1 lead. But now, go ahead and plug this into your KSP expression. So KSP is 1.4 times 10 to the negative 8th. And this equals, now in this case, my lead is x. My iodine is 0.010 plus 2x squared. Go through and do the math. And again, you can take that little shortcut. So we're going to have x, the change in x being negligible. And then when I go ahead and solve for x in this particular case, I get 1.4 times 10 to the negative 4th molarity. So what you're seeing here is how the concentration changes when you have that common ion. Okay, how does this relate to then pH? So you can make things more soluble by either adding an acid or a base. And here, if you want to think about Le Chatelier's principle, how that might work, think about magnesium hydroxide, a solid substance. This is what's used in milk of magnesia when you have an upset stomach to kind of help relieve acid indigestion and that sort of thing. And basically how it kind of works is on this idea of KSP. So magnesium hydroxide is basically insoluble. But if you take this as an acid, keep in mind what's in your stomach is some H ions. So you have a huge amount of H ions. The H ions are going to react with this stuff to form water, right? Which means the concentration of OH is going to go down. And if your concentration of hydroxide ions goes down, concentration of this stuff is going to go up, and this stuff is going to go down, so your overall reaction is going to shift to the right. So this solid stuff that you're ingesting will then dissolve in your stomach and help neutralize the acid. So many different substances kind of work under this same sort of idea. So if you've got a bunch of different salts, and all of these are basically insoluble, according to your solubility rules, what you're going to be asked to do is figure out, well, how will these react if you put it in an acidic environment or a basic environment? Will that help dissolve some of these solutions or dissolve some of these substances? So for instance, if you've got this big old list and you're trying to figure out, will solubility change depending on pH for any of these things, you go back to your hydrolysis idea of what are the parents. So you look at your different salts, like here's an Ag and an F, Ag and Cl, Sr, Is it strong or is it weak? So you look at all your different ions there. The 3 of these that would have an increased solubility based on their pH are going to be AgF, the lead hydroxide, and the strontium nitrite. Okay. Why? Because all of these salts have anions that are basic. So if you think of what F comes from, that might be hydrofluoric acid, which is a weak acid. So the weak acid gives off a conjugate base, so this is more basic. This might come from sodium hydroxide or lead hydroxide or something like that. So the salt, clearly here with the hydroxide, is going to be basic. This is a weak acid, so the conjugate of a weak acid is going to be a base. Why these other ones aren't? Because this AgCl, this is going to be hydrochloric acid, that's strong. This might be nitric acid, that's strong. This is going to be hydrochloric acid again, so that's strong. So changing the pH will not matter for those particular things. Okay, so how do we use this in lab? Well, say you're mixing a bunch of stuff and you're wondering if you're going to create a precipitate with things. There is kind of a breaking point. some solutions, how do you know what the molarities are to make a precipitate? Can you mix things together that should give you a precipitate but it won't? And how you figure that out is the idea of Q. So now we've talked about Q before when we did equilibrium. It's kind of giving you an idea of where are you in relationship to the equilibrium position in relationship to K. So again, we're going to have to compare K to Q. And in this case, we're looking at QSP versus KSP. And just like every other Q expression that we've set up, and every other K expression we've set up, the QSP is set up by doing products over reactants. Okay. If you do the calculations for Q and you find that your Q is greater than KSP, whatever you're working on will form a precipitate. If your Q is less than your KSP, then no precipitate will form. So let's take a look at a sample problem here. 50 milliliters of sodium phosphate mixed with 50 milliliters of barium chloride, and we want to know if a precipitate will form. This KSP refers to the barium phosphate solution here. Let's see, barium, so I'm going to need 2 of those. Oops, that should be 2. Sorry. So that's going to be my barium phosphate. If you think of your overall reaction, barium chloride mixing with sodium phosphate, your solid or your precipitate is going to be barium phosphate. So now I got to think about my solid. And what is that going to be doing? Because it is still in a nice aqueous environment. So I'm going to write out my equilibrium expression. So that's my solid, but these things are aqueous. Now, since I've got 2 different volumes and 2 different molarities, the first thing that you definitely need to know is figure out how many moles of each substance you're dealing with. Remember that sodium is going to be a spectator ion and chlorine is going to be a spectator ion. So what we're going to do is we're going to calculate how many moles of the phosphate we have. And so that just kind of comes from this information, calculate moles. And then I'm going to calculate moles of my barium chloride. So, and I get that from that information here. So this is, oops, that's going to give me this stuff. This is now given me concentrations to stick into my KSP expression. Now the question is saying, will a precipitate form? I don't know. I know a KSP, but I have to calculate my QSP in order to figure out if a precipitate will form. So now that I've gone ahead and calculated my moles of each of the substances, I'm going to plug that in to my QSP expression and see what I come up with. So this is 10 to the -5th, and I want to, oops, 2 there. Okay. I'm going to go ahead and square that. And I come up with a Q answer of 2.7 times 10 to the -22. So this is my QSP value. So now I'm going to compare it to the KSP value, which is up here, 6.0 times 10 to the -39th. In this case, my Q is greater than my K, so yes, a precipitate will form in this particular case. Example number 2, we might have competing precipitates. Sodium chloride is added to a beaker that contains a mixture of lead nitrate and silver nitrate. So let's think first about what are the 2 precipitates that we might get. If I mix sodium chloride with lead nitrate, that's going to give me lead chloride as one of my possible precipitates. If I mix sodium chloride with silver nitrate, silver chloride is going to be my other possible precipitate. So what I want to figure out, if we've got all these solutions together, is which one is going to precipitate out first. So again, another little application of Q versus K. So let's set up our equilibrium expressions. Think about what we have. I have volumes and molarity. So first thing you want to do, calculate moles. Always calculate moles. I don't know the chlorine in this case. Because that's my spectator ion, and really that's, even though it's a spectator ion in both cases, since I'm trying to set up my Q expressions, kind of need to know that little tidbit of information. I only know my concentration of these silvers, so we're going to call those X and X. I know my KSP for lead chloride, in this case, is 1.6 times 10 to the negative fifth. There is a fabulous table in the back of your book where all of these are listed, so if you don't have them readily available, you just have to look them up. Most of the time they're given to you in the problem, but you might have to go fish through the textbook. When you're trying to calculate or figure out which precipitate is going to form first, what we're really trying to do is figure out what are these concentrations of this ion. What are the concentrations, like what is the tipping point of, when do you have enough to make the two different precipitates form? So you can't just always look at just the KSP and decide, oh, this is a bigger number than this number, so maybe the lead chloride will precipitate first. No, you got to look at your molarities and so forth. So let's go ahead and solve for my solubility, my molar solubility of the chlorine ion. So we've got 0.00015. and then 2x squared. And so when I calculate this, x is going to come out to be 1.63 moles per liter. And so that's the concentration of chlorine ions that I need for lead chloride to precipitate. In this case over here, 1.6 times 10 to the negative 10th equals 0.00035x. I solve for x and it comes up to be 4.57 times 10 to the negative 7th moles per liter. So now I'm going to compare these two concentrations. 0.163, 4.57 times 10 to the negative 7th. This is a small number. What this is telling me is that I need less of the chlorine ions in order to create the precipitate. So therefore, silver chloride will precipitate first. PPT is just an abbreviation for precipitate. So that kind of gives you an idea of what types of problems you might be dealing with KSP. So just keep everything in mind about what you've learned about equilibrium, Le Chatelier's principle, and that'll serve you well. Now the last little piece of this chapter talks about qualitative analysis. Hopefully we get time at the end of the semester to do it because it's kind of fun. Basically you get a big soup of stuff and you've got to figure out what kind of ions are in that. And so knowing solubility rules and figuring out precipitates and that sort of thing is really, really helpful in doing qualitative analysis. So this is kind of just a little flow chart. Read through it, kind of get a sense of what's going on and how do we figure it out. But it's a laboratory method in order to separate out different ions and identify what's in this random mixture of stuff. So that part is also in the chapter. The final piece of the chapter is not a huge topic on the AP exam, but worth a little mention because some of the learning objectives do reference things known as complex ions. So I'm just going to throw out some vocabulary words for you here. Just kind of write down the definitions in your notes. And so when you look at these complex ions, hopefully you won't get totally freaked out. You'll be able to take a deep breath and kind of break it apart. So complex ions are usually a metal ion, and it's usually a transition metal, so things like copper and iron. And then they're surrounded by what we call ligands, these other pieces. Now why this is kind of important, or why this kind of comes into play and why it happens, is because transition metals have those d block orbitals. They have those 3d, 4d, 5d electron orbitals available. So that's why they can also make multiple oxidation states, copper 2 versus copper 1, iron 3 versus iron 2, those types of things. And because they have that, transition metals make very pretty colors, blue and purples and reds, and not really reds, yellows and oranges and that sort of thing. And then they also exhibit what we call paramagnetic behaviors, and it's because they have unpaired electrons, and we'll kind of delve into that a little bit more in other units. What a ligand is a molecule that has a lone electron pair, and it will donate this electron pair to the metal ion. So think about ammonia is probably the easiest one to sort of picture as a ligand. You've got your 3 hydrogens and it's got this lone pair of electrons. So because the transition metal has these d block orbitals in their space, it will bond with these lone pairs of electrons. In terms of vocab, coordination number is just going to kind of help us figure out, well, how many ligands can attach to any one given metal ion. And here's what they look like. So take a deep breath and realize that this really isn't as complex as it looks like. So for this, you've got cobalt with ammonia ions kind of attached around it. And this is my coordination number. It tells me how many ammonias can attach to the cobalt ion. You know, just kind of be familiar with them and realize that's what's going on with this type of stuff. You might see things being named. You are not expected to be able to name these things. Just kind of throwing them out there, so hopefully if you come across them, you'll know what to do with them a little bit. And that is it. Have a great day, guys.